Okay, this is module 7A. We're going to look at the entropy balance and the entropy of mass, how entropy is assigned to mass. Earlier we talked about heat carrying entropy. Now we'll talk about how entropy is carried in or out of a system with mass or stored with mass by this. Talk about the entropy balance. The entropy is in plus generated. It's balanced. In plus generated equals out plus accumulated plus consumed. The second law of thermo says that entropy cannot be consumed, it can only be generated. In fact, the generated term is always positive. So entropy generated, positive number. That's really the most concise statement of the second law, mathematically. Entropy of heat, you recall, is Q over T. Q over T is entropy carried by heat. The entropy of work is 0 because if you took heat, you could turn it into, if you took work, you could turn it into heat of the highest possible temperature. So that would be Q over, let's say, infinity, which would be 0. Now let's look at how entropy is added to mass. If I take heat and add it to the mass, then I'm going to call this a small flow, call this a little del Q, a small flow of heat over temperature is equal to the mass times the ds, the change in its specific entropy. And that's for a reversible heat flow, one occurring at constant temperature where there are no gradients in temperature. So if we solve this on a per mass basis, take a small q to be heat per mass, then ds, the specific entropy, would be dq over t, or little del q is equal to t ds. Now we'll apply an energy balance, in equals out plus accumulated, and we'll add some heat to the system, take some work out of it. So Qin equals work out plus the mass times U final minus U initial. Actually, those should be lowercase u's, specific internal energy. Or if I take and divide out the mass, then I'll have per mass Qin equals work out plus delta U, where delta U is the specific internal energy change. Or, shrinking it down, dq is equal to dw plus du, or a small, actually that's a small flow of heat, equals a small flow of work plus du, the change in the property internal energy. Now if you recall, dw, if it's work out, is equal to p dv, where dv is the specific volume, plus du, dq p dv plus du. And that's for a reversible case where P is the pressure of the system, P internal equal to P external. So the work you're exporting, P external dV is equal to the work being done, P internal dV. No gradients. No gradients makes it reversible. For reversible heat and work, then, we have TdS equals PdV plus du. Or solving it the other way, du equals TdS minus PdV. And that's the way you'll commonly see it. This is called the fundamental property equation. Fundamental property equation. You see, we just got it from taking the definition of entropy, dq over t, applying it to a system and doing an energy balance on the system, and an entropy balance. For a reversible system, we have du equals TdS minus PdV. But now we're talking about properties because du is a property, ds is a property, v is a property. So we're looking at a property-only equation, and a property-only equation does not depend on the path, whether it was reversible or irreversible, how it worked. So this equation applies to all processes. du equals TdS minus PdV. If we take an ideal gas now and apply this equation, du is equal to Cv dt, which is also equal to TdS minus PdV. And manipulating that around a little bit, we find that ds, and we're trying to find change in entropy for an ideal gas, Cv over T dt plus P over T dV. since it's an ideal gas, PV, and here's specific volume, is equal to RT over molecular weight, RU over molecular weight times T is equal to P times V. Solving this, we wind up with ds equals CV over T dt plus RU over molecular weight dV over V. Now I suggest that at this point you stop, do the algebra, convince yourself that all this is true. Now let's look at the entropy change due to a phase change occurring at constant T and P. Now that's, for instance, when you're boiling water at a constant temperature or at a constant pressure. If one is fixed, the other must be fixed also as long as you're in the saturated state. You recall that. So suppose we're changing phase at constant temperature and pressure. And we pull out our fundamental property equation, du equals TdS minus PdV, and solve it for ds. Then ds is equal to du over t plus p over t dv. But dH equals du plus d of pv, because recall h is defined as u plus pv. So dH equals du plus p dv if it's occurring at constant p. Hence dH over t is equal to du plus p dv over t, and that's equal to ds. So ds is simply dH over t, or delta S of vaporization is equal to delta H of vaporization over T. And you recall that in your steam tables, delta H of vaporization, the enthalpy of the gas minus the enthalpy of the liquid, is simply called HFG. Let's take a look at a little example. Suppose I want to find delta S of water from a saturated liquid at 1 bar to a superheated vapor at 200 degrees C and 1 bar. So first we'll find delta S of vaporization. If you look in your steam tables, you'll find that should be approximately this. It depends on the tables you're using, but should be approximately 2258 HFG at 1 bar. Plus, and that's divided by, you've got to be careful because the tables will give you T in degrees centigrade. Add the 273.15 to get it to Kelvin. Anytime you're dividing by T, it's almost always going to be that you need to have absolute temperature. If it makes a difference when you're doing the calculation, you're safer using absolute temperature. And nature considers temperature, the absolute temperature, the one that matters. So this comes out to 6.0572 kilojoules per kilogram K. And if you look in your tables, you'll find that that should be very close to SFG at that point. So HFG over T, and that's going from a liquid to a vapor at 1 bar, but now we're at 1 bar and 99.63 degrees C. So we have to bring it up from that state to a superheated vapor to find the total change in entropy. So here's how we'll do it. We'll take delta S of the gas, now that's become a vapor, equals the integral of CV dt over T plus the integral of RU over molecular weight dV over V, or that equals to CV ln of T2 over T1 plus R molecular weight ln of V2 over V1. And we'll plug in the values for V1 and V2 and T1 and T2. In order to do this, of course, you'd have to find the volume at the higher temperature. And to do that, you would use the ideal gas equation. So a few calculations involved here. I suggest, again, you stop at this point, go through the calculations, and find this total. If I add those two terms together, then delta S of the gas going from the first temperature to the second temperature is equal to 0.4486 kilojoules per kilogram K. And this is primarily to show you how entropy, just using the basic definition of entropy, Q over T, and the fundamental property equation, which we derived from an energy balance and an entropy balance on a reversible system, yet applies to a non-reversible system, then we'll get the delta S. And here we have, and you can compare that to data in your tables. So here we have delta S total, 6.0752, that's for vaporization, plus 0.4486, that's for raising the temperature, is equal to 6.5 kilojoules per kilogram K. If we go to our tables, we find that S at a pressure of 1 and a quality of 0, that's our saturated liquid at 1 bar, 1.3026. Now we'll look in our superheated tables. S at a pressure of 1 and a temperature of 200 for our superheated vapor is 7.8343. Take the difference, and we find that delta S in the tables is 6.5317, and we found 6.5058. So we've got it very close. There are some differences based on assuming, first of all, that it was an ideal gas. The pressure is pretty low, so it should be an ideal gas, but also we took a value of CV that could be changing. If we wanted to be more precise, we could integrate it and get even closer numbers, closer values. So calculating it with equations or looking it up from your tables, very much the same value. Okay, now we have an idea how entropies are assigned to mass. So in summary, what we've done, what we have, in fact, so far, for the first law and second law, we can do an energy balance. There's your first law of thermo, or an entropy balance, second law of thermo. And then the terms that commonly come into these balances for thermodynamic systems, Q, W, H, and U for the energy balance. So when we have heat coming in, that's just Q. The entropy balance, Q over T. For work, it's just work. That's energy. And remember, work carries no entropy, so we have a 0 here in the entropy balance. For mass in or mass out, that mass times H, remember, H is U plus PV, so when a mass is coming into the system, its energy is both its internal energy plus the flow work to bring it in, so that's PV. A convenience property H takes care of both of those. And for the entropy balance, we simply use the specific entropy S. And for the mass of the system, if it stays in the system, then there's no flow work to be concerned about, so the energy balance we have U, the entropy balance we have just S. Of course, we're neglecting kinetic energy and potential energy at this point. Those could be added to the energy balance, but because they're mechanical energy type terms, they have the same ability to be turned into heat of infinite temperature, and they'll carry no entropy either. So if you need to add kinetic energy, potential energy, you can do so with the energy balance, but they don't belong in the entropy balance. Let's take an example. Heat is available at 200 degrees C. And what's the maximum amount of air that can be heated from 100 degrees C using 1 kilowatt of 200 degrees C heat, taking 1 kilowatt from a 200 degrees C reservoir, let's call it, given that the surroundings, that's another large heat reservoir, are available to you at 30 degrees C. So let's draw our system out. Suppose I have Q coming in, QH coming in. That's 1 kilowatt that we're given. And I want to know how much air I can bring in from 30 degrees and heat up to 100 degrees C. Remembering that I could pull in some heat from the surroundings to help me do this. Usually don't think of that, but it's possible to do this. So we'll treat this as a sort of a black box, and we'll just look at the things coming in and things coming out, do an energy balance, an entropy balance, and find out what's possible. For the energy balance, QL plus QH equals plus M, so the two heats coming in plus the mass times HN equals the mass times H out. Since we have an ideal gas, we'll treat air as an ideal gas. Then we'll substitute Cp delta T for delta H. Then we'll do our entropy balance. Q low over T plus Q high over T plus S generated equals mass times Cp ln of T2 over T1. We're assuming that the pressure is not changing. So you recall there's two equations, one we just derived for change of entropy of an ideal gas, and then there's one that uses Cp. Recall Cp ln of T2 over T1 minus R over molecular weight ln of P2 over P1. The pressure is not changing, so that part will drop out, and you only have the temperature change to be concerned with. And we're going to consider this. I asked you to find the maximum amount of heat of air that can be heated. When we're talking about the best we can do, we need to make that entropy generated go to 0. So this whole term is going to drop out. Set that to 0. Solve the two equations simultaneously, the energy and entropy balance. And QH is given. So the result is QL 2.58 kilowatts. Now that's great. We brought in 2.58 kilowatts. Think of that as almost free energy from the surroundings. And that 1 kilowatt that we had at the high temperature we also used, so we're managing to squeeze in really 3.58 kilowatts into that air. With that, we can heat the air. We can heat 0.0509 mass units of air. Now, that what we just looked at was the best we could do with any system any engineer could devise. Now we're looking at a simple heat exchanger, how much air could be heated. Here's our system, mass coming in, heat added. We're not trying to pull anything from the surroundings. So that heat is all we have, that 1 kilowatt. Energy balance is very simple. QH equals mass times Cp times delta T. We get 0.0142. As you recall, earlier we had mass was 0.0509, something like that. So we really get more than 3 times as much air in the ideal process. And with a simple heat exchanger, we get a lot less. So there's always the potential. Thermodynamics allows you to set a bound on what's possible. It's up to the engineer to figure out how to do it. So really, we have a simple, efficient heat exchanger here. We can heat 0.0142 units of air with that. Or we have a very complex sort of device that hasn't yet been discovered that would use turbines, pistons, cylinders, you name it, all kind of equipment. And somehow we managed to get more done with it, which makes it more efficient. So again, thermo sets limits on what you can do, and the engineer must work to achieve a cost-effective solution to this problem. Now I'll tell you, if we assumed reversibility for this complex system over here, for it to be reversible, you recall the gradients have to be approaching 0. So this system on the right is going to be extremely large, very expensive. Well, if you really approach it, you really never get to complete reversibility, but if you did, it would cost a lot. So you're really balancing the operating cost of not being able to heat as much air with this heat exchanger with the capital cost of spending more on the equipment but being able to do more with it. So it's usually a cost benefit that engineers go for. Okay, let's take another example. Suppose an inventor claims he can produce 600 kilowatts of work from 800 kilowatts of heat. The heat comes in at 700 degrees and the environment's at 30 degrees. Is his claim reasonable? Well, let's look at it. QH coming in at 700, QL going out at 30. One of the implications of the second law is that you cannot turn heat completely into work. You always have to have some waste heat. So let's take a look at his device. Now you see what I'm doing here. I'm putting these temperatures into Kelvin because you're always using, if it's Q over T, we're always using absolute temperature, so be careful with that. Energy balance Q equals QH equals W plus QL, in equals out. Plug in the numbers, and in this case we have enough information to calculate S generated from his claim, so we can calculate what QL is. It must be 200. And so we'll calculate S generated, and when we do, we find out that it is negative. And if S generated is negative, you cannot, it just won't work. It just won't work. It violates the second law of thermo. So we can, now, if we want to use S generated to quantify irreversibility, we can say that an S generated greater than 0 is an irreversible process, and that's really all the processes. That's all real processes are irreversible. Now in the limit, if S generated is equal to 0, we have what's called a reversible process, and you know we've talked about that happens when there's no gradient. And of course, if there's no gradient, nothing ever happens. Nothing to push it forward, nothing will ever happen. So it is an idealization. Of course, if you calculate S generated and you find it's less than 0, as with that last example, then of course we have an impossible process. It's never been proven to have a process where S generated is less than 0. Okay, the flow across a gradient causes the irreversibility. And I just want to point out that this happens with all kinds of flows. A current flow, a fluid flow, a current flow due to voltage, a fluid flow due to pressure, a heat flow due to temperature, or a diffusion mass flow due to concentration. And irreversible, anything that cannot be turned around to flow the other way spontaneously is irreversible. Water falling downhill, heat flowing from hot to low, and so on. If it wouldn't happen spontaneously the other way, then it's irreversible. Let's give you some examples. An inelastic collision. A car runs into a tree. That's obviously irreversible. You've got problems after that. Solid state friction. Just scratching across the ground. You're turning work into heat. Shock waves. A spontaneous chemical reaction. A flame, something like that. It's hard to go back. If you strike a match, it's hard to take that and turn it around and go back to the sulfur and the match. Mixing of different species. Anytime you mix two things together, if I put dye into a liquid water, drop a few drops of food coloring into it. Now how are you going to make that go back the other way? You're not, unless you put some work in to make it happen. Other examples, internal damping of a vibrating system, say the shock absorber on your car. You go over a railroad track and the car bounces up and down. Well, that's because your shock absorber is not working too great. If you put a shock absorber in there, then all the energy that would be into vibrating or bouncing the system is absorbed into the shock absorber. That energy is absorbed in there, and you can't get it back as mechanical energy without doing some other kind of work. Unrestrained expansion of a fluid through a valve. Passing a fluid from a high pressure to low pressure, and that's something we'll look at quite a bit in thermo. Going through a valve is highly irreversible. You drop the pressure. You went from a high mechanical potential, a high pressure, to a low pressure, and you got nothing for it. That's irreversible. Osmosis, water flowing downhill in concentration. So the entropy balance, to summarize, can be carried by heat. Entropy can carry by heat or by mass. Entropy is generated by irreversible processes. We looked at how we calculated the entropy of mass. It came from the idea that you add heat reversibly, and we came up with this fundamental property equation that gives us how ds is determined. The entropy change of mass is assigned by reversible heat interaction, and then we go from there. Homework. Okay, read Chapter 7, Sections 1 through 9. In this course, I think you can skip the variable-specific heat analysis. If you're a mechanical engineer, you want to take a close look at that because you'll use it for your next course. If you're a chemical engineer, we're going to take care of variable-specific heats by integrating them. But for now, I want to just assume constant specific heats To get a more precise answer, you might take a specific heat that's an average over the temperature of the process that you're working with. So work the problems with answers through 797, and that should catch you up.